All right then. So in the last lecture, actually we went through a number of things, didn't we? We looked at the chemical potential, and I tried to sort of start from the official thermodynamic definition of that and sort of take you through in a sort of slightly sort of graphical way as to what that actually means, and try to connect that to what we looked at in the first lecture in terms of plots of Gibbs free energy versus composition for this binary solid state solution. And so we looked at activities and activity coefficients and looked at that, and then went on to diffusion and saw how free energy is provides the driving force for diffusion, but how that doesn't always happen as you expect. In other words, if you remember, if you have a miscibility gap, then within the miscibility gap you observe something called uphill diffusion, where actually the components of a binary solid solution will diffuse up the concentration gradient, and that of course is because actually it's the chemical potential which is providing the diffusion potential rather than just concentration. And then I went and we did a little derivation of modified Fick's law, which I'm just going to write down again now. That was the flux for some species of atoms I, the number of atoms crossing a unit area per unit time, and saw that that was equal to minus some coefficient to do with mobility, the drift velocity, if you remember, resulting from the driving force, times the concentration of that species times the gradient of the chemical potential of that species. So we looked at that and compared that with what you'd get in the case of electrical charge, and saw that this is just sort of the analogy of Ohm's law, if you like, and then generalized that to the idea of fluxes with conjugate forces and linear relationships between those. So we have chemical potentials for the diffusion of matter, we have electrostatic potentials for charge and current, and we have temperature gradients for the flow of heat. And then more rapidly towards the end we talked about the coupling between those things, and looked at thermoelectric effects, in particular the Seebeck effect, which is how you operate a thermocouple, and the Peltier effect, where you can provide refrigeration, if you like, just with an electrical current. And I did that fairly quickly, and there is also a problem about that on the first problem sheet. So I suggest if you have questions about that, if you want to revisit that, I suggest we can do that in the first rapid feedback session, where we look at the outcome of that first problem sheet, if you want to spend a bit more time just trying to dig a bit deeper into that. But today I'd like to sort of move on to our second big topic, which is really about diffusion, and that's why we're starting again with this modified Fick's law here. So so there it is with the chemical potential, and the chemical potential we've said we can write in the following form. So I'm going to write an activity coefficient there, okay, which multiplies the concentration, which I'm going to write not now as a mole fraction, but as a normal concentration. So C is number of atoms per unit volume, and then if I want to make it molar, I could multiply that by the volume occupied by a mole. You'll see in a second that doesn't matter. This is a log of a product, okay. Here, this is a constant, so I can write it as the log of that plus the log of that plus the log of that. And when I take the gradient, then clearly a constant multiplicative term inside here is going to be actually the derivative of a constant additive term, so it will just go to zero. It will not make any difference to what we're trying to do here. So, because of that, the gradient of mu I from place to place, the first term is a constant. So I've got RT, and I'm going to get the log of the gradient of the activity coefficient divided by itself plus the gradient of the concentration divided by itself, and then there would be another term which was the gradient of the V molar, which is a constant, so that's 0. Just to write a little bit in here just to make sure that's clear. Okay, so I've taken the gradient of that expression. Now, if gamma I is a constant, if the activity coefficient is a constant in space, okay, then its gradient would be 0. It will be a constant in space if it's a constant with composition, because composition is what actually varies in space. And the activity coefficient actually sort of depends on the concentrations. Remember that graph I showed you of how the activity coefficient varies with concentration as mole fraction from 0 to 1. So any gradient here, any spatial gradient of activity coefficient would arise from a spatial variation in the composition and an activity coefficient that depends on composition. Okay? So here we can say that if gamma is constant, that is, what do we call that law? Anyone remember? What were the two we looked at? Henry, yeah, or Henri. Do we think he's? I think he's French, so I think it's probably like Thierry, Henri. Okay, so that is Henri's law, which was that the activity coefficient is a constant. A special case of Henri's law was Raoult's law about an ideal solution where the activity coefficient is a constant and equals 1. So this includes both of those cases. And certainly we know this is always true when you're close to pure A or pure B. Okay, this situation definitely occurs there. Probably doesn't occur so much sort of in the middle. But if that's the case, then that means, of course, then that this first term vanishes. So we've only got this second term here. So plug that into there. Okay. So if that is the case, then Ji is minus this mobility tensor times R times T times the gradient of concentration. Okay, which we might call minus D I. Okay, so we wrap up these constants here into another one, which funnily enough is going to be the diffusivity, and this of course is fixed first law in its most popular form. So flux is proportional to concentration gradient, like that. Okay, so what's important just to stress here is that this is not simply true. This doesn't simply hold in the case of an ideal solution where gamma is 1 and therefore the activity is the concentration. Okay, it doesn't just hold there. It holds in a slightly more general set of situations due to Henri there. Okay, so we've got a fixed first law there. Do you know what else the diffusion equation depends on? That's the first thing, this fixed first law. Do you know what the second thing is that's built into the diffusion equation? Fundamental principle of physics. Conservation of matter, exactly. So what does that mean? That means for for any closed volume V, we must have, if we do a surface integral over the boundary of that volume V, that's what I call sort of curly dV, it means the surface, the closed surface, which is bounding the volume V, and then I write that, okay? So it's like Gauss's law or something like that, isn't it? It's a flux, which is amount of matter per unit area per unit time, integrated over an area. So it's the amount of matter per unit time flowing through the boundary of this volume V. And if I've taken my convention such that the element of surface area always points outward from the volume, then this is the next flux out. Okay? And that must be, so that's per unit time, that must equal the rate of change of the total amount of stuff inside the volume. So I take the concentration integrated over the volume, that's the total amount of stuff inside the volume V, and d by dt is the rate of change of that per unit time. So the dimensions of left and right are the same, and there's a minus sign there too, because obviously if this is an outward flux, that must be leading to a reduction of amount of stuff inside the volume. Okay, so you've got a continuity equation there, and of course you can apply the divergence theorem to the left hand side and then get that must be the integral of the divergence of the flux. Okay, and this is true for all volumes. Okay, it was for any closed volume there, so therefore that means it must be obeyed on a pointwise basis. That must be true. Okay. The only reason that would not be true, if there were a source or sink of material within your volume V, something that can somehow generate more material or, annihilate more material, which we might think no, we're not going to have that sort of thing. Matter can't be created or destroyed. Whether you have a little pipe in there or some other sort of mechanism to feed something in there, maybe there are sort of slightly contrived situations where that it might be useful to pretend you have something like that, but generally speaking you don't. So that is true, and therefore, okay, now we put those two things together. So the divergence of the flux is the divergence of from Fick's first law, the diffusivity times the gradient of the concentration. We can cancel the minus signs on both sides, and then we've got the divergence of diffusivity times concentration. Okay. Now, just think about this diffusivity here. In general, I've put it down as a tensor, and it could well be anisotropic if my material is not isotropic, if it's not cubic, not a cubic system. Then there's no reason why the diffusivity. I think of some obvious examples of that. Graphite. Think about graphite. You've got these infinite two-dimensional sheets of carbon atoms. Clearly, the right sort of atom that is sort of sitting in there between two sheets can diffuse pretty rapidly in the plane of the sheets between two of them. Its diffusion perpendicular is going to be much slower. So that's an obvious example. So in other words, the sort of the properties of this tensor will reflect the properties of the structure of the material. Diffusivity. What else does diffusivity depend on? Sorry? Temperature. Yeah, absolutely. Generally speaking, diffusion is an activated process. It's going to be heavily temperature dependent. I mean, you can see that we wrapped a we were apt to factor a temperature into it anyway, but actually there's an exponential dependence in here, which is much more significant. So if temperature depends on space, then diffusivity will depend upon space, and then there'll be some spatial dependency on this thing here. Okay? So it won't be a constant in space. Could depend on concentration. Yeah. There could be that, you know, you could imagine situations where that could be the case. So sometimes if you have, we'll look at this a bit later, but sometimes you have atoms like carbon in iron. When you have steel, the carbon tends to sit, because it's a relatively small atom, tends to sit in sort of little interstitial sites between the iron atoms, but it doesn't quite sit there. It sort of is a bit squashed, so it tends to push back on that. It will tend to sort of induce a bit of strain on the surrounding lattice, create an increasing amount of space. If you imagine you had a sizable concentration of carbon, then you've got quite a lot of these points where the carbon atoms are just pushing the iron lattice apart. And so generally speaking, they will just sort of jack it open. That means that the space between the carbon atoms is more open, and then carbon may more rapidly diffuse through those. So the concentration of the diffusing species can actually have an impact on its diffusivity. And so, again, through there you might have some spatial dependence. We start with the easy thing. If we say that D, if we assume it's isotropic, what does that mean? That means that, sorry, I'm going to just, that's not very helpful notation for you actually. Do that again. Di, and then components alpha beta, Cartesian components alpha beta, because it's a tensor property here, is a scalar di times the Kronecker delta alpha beta, like that. Then in those situations I can, so it may still depend on space, but essentially there is an expansion now that I can write. Okay, on the left hand side, so you can see that you've got two terms there. Hold on, there shouldn't be minus signs here. Okay, the minus sign there cancelled with the minus sign there, so there shouldn't be a minus sign there. Okay, that's what's going on. And if D, well, it's now scalar D, is spatially uniform, that means that the gradient of Di is naught. Then you end up with that. Okay? Which is probably the form of the diffusion equation that you would have written down if you were asked to, is that right? But now you've seen sort of where it's come from our beginning of where we sort of started from looking at the modified Fick's first law, and you can see the series of approximations that you have to make along the way. It's quite important to understand what all of the approximations or assumptions are that you have to make in order to land up with this equation, because there are quite a few of them. Okay, so that's quite important. Now let's just ask ourselves what that means. Yeah.
D is a tangent.
Yes.
How do you differentiate?
In here.
There's only one index.
Sorry, the index I.
The index is that.
The index I is the species of the atom, and alpha and beta are x and y, x, y, z. So here I've just put it in without any indices, same as vector, and then I've labelled the components alpha and beta.
You just say it's diagonal.
Yes, that's saying it's diagonal. Are you familiar with that Kronecker delta? Yeah. So in other words, it's just diagonal and it's got the same element, di, of all three elements of the diagonal. Yeah.
The last line, are you saying it's isotropic as well as stationary?
Yes. Yes. And yes.
Thanks.
Okay. You have to have both of those things in there. Good questions. Right. Let's just have a look in one dimension. Okay. Let's imagine that we've got a variation of concentration like that. The left-hand side is just the second spatial derivative with respect to x of c in this case. And the point is here, okay, there's going to be a point of inflection about here. And to the left of this is concave down. Okay, so d2c by dx squared here is less than naught. And so the second spatial derivative is negative, which means that the partial derivative with respect to time must be negative, and therefore that means that the concentration must be decreasing there. Whereas over here you've got the other situation with concave up, positive second derivative, increasing with respect to time. And so you can see what happens over time, that again, as you would normally expect in diffusion, you get a sort of, it evens out the spatial variations and tends to lead to a constant concentration across. So that's how the diffusion equation is working. And what's of course very important is that this is a linear partial differential equation. Yeah? At least if d is a constant. Why is that important? You can add solutions together. You can always do linear superposition of a linear one. And that's what we're going to exploit a lot now, okay, when we actually get on to solving the thing. Okay, so that sort of got to the end of we've now derived the diffusion equation. We'll derive it again another way later, but we derived it here with a sort of continuum view of things. Let's think about trying to solve it now. So, the first thing I'm going to consider are steady state solutions. Okay? In a steady state solution, that means that J is constant in time and there is no change with respect to time of the concentration. So in other words, the right hand side of the diffusion equation vanishes, and I'm only going to consider one component now for simplicity. So your solutions are harmonic functions, which is what we call a solution of Laplace's equation. Okay? Which is what that is. So, these are now ordinary differential equations in one dimension. The second spatial derivative, which is a total derivative, is now 0. And we're going to consider an infinite plate. Okay, so of course this isn't really in one dimension. What I mean when I say I'm solving it in one dimension, what I mean is that there's no variation of any quantity in the y or z directions. And the y or z directions here are the ones that are in the plane of this infinite plate. And I'm going to assume this has got a width, big L. And I'm going to have a constant concentration. I'm going to maintain a constant concentration C0 at x equals 0. So on this side of the plate, and I'm going to maintain a different concentration C1, okay, on the other side of the plate. So if you want to write that down, what does that mean? That means that the concentration for x is 0 and all times is C0, and the concentration on the other side at all times is C1. How would you solve this? Trial solution. Yeah, normally you think of your trial solution and exponential. If you do that, you'll get one of those special cases. Yeah? Okay, it's a linear function. Yeah, so that's what you'll get out. If you follow the standard recipe for second order ordinary differential equation with exponential trial solutions, you'll find that it's one of those things where the auxiliary equation has a repeated root. Okay, and that the exponent is 0. Okay, but you don't actually need to do that in this case. This is a method for solve. I know when you're taught ordinary differential equations from the very beginning, the first thing you're taught is the second order one normally, and the exponential ansatz. But actually, sometimes you don't need to guess with the differential equation. Sometimes you can just do it. In this case, I can just integrate both sides with respect to x. So you integrate the first side with respect to x, and you get dc by dx is a constant. Yeah? So I can get dc by dx is a constant, which I'll call k1. And then I can integrate that again, and I'll get c is k1x plus k0. Is that okay? Yeah? Now, and then you put the balance, so that tells you it's a straight line. No guessing there. I know that when x is 0, at x is 0, the concentration has to be C0, and that x is 0, so K0 has to be C0, and when x is L, C1 has to be K1L plus C0, and therefore K1 is just simply got to be C1 minus C0 over L, and therefore the concentration can just be written like that. Okay? So that's solved. That solves your problem, matches your boundary conditions. If I go and plot that out from 0 to L in x. So if we take the case where C1 is greater than C0, okay, the concentration is higher on the right than on the left. That means we're expecting the material to flow from the right to the left. Our solution must look like that. Okay, the flux here, J, is minus d grad of the concentration, which is just dc by dx, and of course dc by dx is just k1, and so this is minus d c1 minus c0 over L. So the flux has got a minus sign. C1 is greater than C0, so the numerator here is positive. So everything here is positive, but it's just got a minus sign. So that tells you that the flux is negative, so actually stuff is going to be moving from right to left, which is correct. And you also see that the flux is constant, okay, throughout the sample, which is exactly what you would expect, right? If the flux were not constant throughout the sample here, if it were greater, if I'm looking in the middle of the sample now and the flux is greater here than it is here, then there must be a build-up of stuff in here, which is not allowed. Okay? Not in steady state. We're not allowed to have any change in concentration with respect to time, and therefore that's why we've got that expression there. Okay? That was easy, wasn't it? Very easy. Right. Let's go to 2D, and let's go to a cylindrical case. Okay, so what I'm now going to consider is is that okay? That drawing not too bad. I'm going to say we're going to maintain a concentration C0 here on this surface of this inner cylinder, and we're going to maintain a concentration C1 on the outer surface. My cylindrical polar coordinates, I like to call cylindrical polar coordinates rho, phi and z. Okay, so z is the axis. Rho I prefer to r to avoid confusion with spherical polars. Is that all right? And phi for consistency with spherical polars because it's the same azimuthal angle. Now, the cylindrical symmetry, of course, means that there is no dependence of phi or z of the concentration here. Is that clear? Okay. The system itself has that symmetry. I can rotate it around the z-axis and it's invariant, or I can translate it parallel to the z-axis and nothing changes. So the solution cannot break that symmetry. The solution cannot have a dependence on phi or z, because also the boundary conditions respect that symmetry. Okay, so it turns out that concentration is a function of rho only, and therefore Laplace's equation becomes 1 over rho d by d rho of rho dc by d rho equals 0. Okay. And now see, I solved this the same way that I solved the previous one. First of all, I can multiply rho on each side. Okay? And then I can integrate both sides with respect to rho. So rho dc by d rho is now equal to K1. And then I have to divide both sides by rho. And then I can integrate up again. Okay, and I get that. Okay, and then I put my boundary conditions in. So for the inner cylinder of radius rho 0, and the outer cylinder okay. So you now want to solve this. Clearly, if you subtract those two equations, you'll cancel the K0. Okay, so C1 minus C0, subtracting the first from the second, is K1 log rho 1 minus K1 log rho 0. That. Okay. If I want to do the other ones, then I need to multiply let me just tell you what I would do. This equation here, I need to multiply, in order to get these two terms to cancel when I subtract, I need to multiply this term by log rho 1. So I multiply this whole equation by log rho 1, and I multiply this equation by log rho 0. And then these two terms will then both be K1 log rho 0 log rho 1, and I subtract. Okay, so I'll get K0 into, writing the second one down, first log rho naught minus log rho 1 equals C1 log rho naught C1 log rho 1. So that gives us K naught is C1 log rho naught minus C naught log rho 1 divided by log rho naught over log rho 1, and K1 is C1 minus C naught over log rho 1 over log rho naught. Okay, and if I now go and stick those back in, I'll get the concentration is 1 over this common factor. I've got some concentration terms, C1 minus C naught log rho, hold on, not quite, I've got a minus sign. Just rewrite what's in there. Sorry, can you see that? Let me just see what I've done. That's upside down from that. So there's a minus sign associated with those that I just need to get right. There we go. Like that, plus C naught log rho 1 minus C1 log rho naught. Okay, that's your final expression, which is perhaps a little bit more complicated than you might have expected. Okay. So if C1 is greater than C naught again, concentration is higher, so that means that this term is positive here, and rho 1 is bigger than rho naught, so this term outside is positive. This term here is definitely got a positive coefficient in front here. The flux, I'll just come up to this space here. So let's just take this and now take this up here. J, remember, is minus D times the gradient of the concentration, which is dC by d rho. You either differentiate that or go back to the expression up here, where dC by d rho was K1 over rho, and just substitute in the value of K1. This is minus D C1 minus C0 over log rho 1 over rho 0 times 1 over rho. So remember, we said C1 is greater than C0. This is positive as well. So J, again, the flux, J has got the sense from out to in, because the concentration is higher outside than inside. But now the flux is not constant anymore through the sample. The flux depends upon 1 over rho. So we have that J is proportional to 1 over rho, or rho J is a constant. Why is that? Exactly. Okay. If I considered a fictional cylindrical surface, a bit like a Gaussian surface in electrostatics, that was coaxial with this cylinder and had some radius between rho 0 and rho 1, and I were to ask myself now how many atoms per unit time flow through this, then that cylinder would have a surface area, a curved surface area, which was 2 pi times its radius times a unit length, let's say. Yeah? And so, actually, if I write in a 2 pi there, you can see, therefore, that the amount of material per unit time is a constant regardless of the radius that I take. Okay, so if I take that imaginary cylindrical surface that varies in any value between ρ0 and ρ1, the amount of stuff flowing through it, the rate at which matter is flowing through it, is a constant regardless of it. That's why the flux has to decay like 1 over ρ, okay, essentially to maintain that conservation of matter. And of course, you could do the same thing for spherical polars as well. I'm not going to do it now. Obviously, exactly the same approach would work. And you now know what to expect. You know that the flux will be like 1 over r squared. Yeah? So that 4 pi r squared j is a constant there. Okay? All right? Any questions about the steady state? The steady state is kind of a not very interesting thing, but it would be kind of silly just to skip it and not give it any time at all. But hopefully that's fairly straightforward. Obviously what's more interesting is when things actually change in time. Let's consider we now want time varying. If I have fixed boundary conditions, and, well, at least a semi-finite, I'm not quite sure really that word has any meaning. Semi-finite domain, by that I mean that there is at least in one dimension, it doesn't just go to infinity. What method would you use to solve this? Well, what methods do you know for solving the diffusion equation? Separation of variables. Who's heard of separation of variables? Anyone not heard of it? No, everyone's hand went up. Quite important. Everyone's heard of separation of variables. You need to nod really hard, because otherwise you're going to get a boring 1 hour lecture on separation of variables, which you haven't done. But if you have done it, I want to know so that I can talk to you about it another time. Okay? If you haven't done it, come and talk to me. But remember, how many of you? Let me ask you a different question. Is that question about heat diffusion along a one-dimensional fixed rod still one of the interview questions for the CBT? Who did that as their interview question for the CBT? Diffusion of heat along a one-dimensional rod. 3 of you did it. 4?
I did it because I thought all 3 questions were going to be asked.
Okay.
I didn't know which I thought.
Other people chose particle in the box. Is that still one of them? Who chose particle in the box? Who chose the bending beam? Nobody chose bending beam.
I did, yeah. I guess that.
You had to do that as well because you thought they were all going to get done.
I don't think I could choose.
Okay. Well. Okay. The method of separation of variables. So if we have, let's just write out. Here's my diffusion equation for one dimension in space, but also in time. And the solution you try, of course, is that you have a go at trying a product of the 2 functions, and it goes from there. Okay? If I were in... Let me ask you this question. Would this approach work in cylindrical polar coordinates? Yeah, it would. Do you happen to know what equation you get for the rho component, assuming we said there was no angular dependence, so there's no phi dependence and no z dependence? Do you know what you'd get, what equation you'd end up for the radial bit? Probably get Bessel's equation, which is a bit nasty. Okay. Spherical polars, it would work. In the angular bit, you get some Legendre. Yeah, you get some Legendre or some associated Legendre if you had dependence on the angular, variables, theta and phi. But if you didn't have any dependence on those, you wouldn't need to worry about that because it would be spherically symmetric concentration, so it would only depend on R. You would get a different equation to solve here, right? So if it were, it would be d over r squared, d by dr of r squared dc by dr. It would look like that. Yeah, because that's the part of the Laplacian for the radial variable in spherical polar coordinates. And obviously the idea of putting, okay, so if I write C of R and T is big R of R, big T of T, then as ever we would end up with d of R squared. The derivatives with respect to R don't operate on big T of T, so you could take that out the front, and this would become d by dr of R squared, big R by dr, and that would equal big R of little r dt by dt. And then as usual you would say you would divide by big R times big T, and the left hand side would depend on big R and little r only, and the right hand side would depend on big T and little t only, so both of those must be equal to a constant. Let me just check something with you actually. Let me just write this, sorry, d over r squared okay. How would you write that constant? How would you write this separation constant? Both left and right have to equal a constant. So how would I write it? This is you know, this is not a life or death situation. This is called trying to make life easy. What's this going to give us? This is equals a constant. So what's this solution always going to be? It's always going to be an exponential. Yeah? It's always going to be big T is always going to be e to the separation constant times little t. Right? So that's easy. The time varying bit is always easy. What could I choose the separation constant to be here to make life easier here, do you think? What do you think this exponent is going to be? So it's exponential. What happens as time progresses? Okay, concentration diffuses. What does that mean? If I've got a
positive, that would be a positive constant, so the positive squared.
You want this to be positive?
No, you want it to be negative. So
I want this to be negative, don't I?
Yeah, to decay.
So that the concentration decays with time. If it goes like e to the plus constant times time, that would mean the concentration was increasing exponentially, and there's no way that that could be compatible with conserving a matter. So it has to decay exponentially with time. So this separation constant better be negative. Okay, so to make it negative, I write it as minus something squared was what you said. Anything else you want to do? Here's my top tip. Okay, so that's what you should do. That will make life if you were doing that in the Cartesian example, right? Then k would just be the thing that appeared in your sines and your cosines, right? It would just look like sine kx and cos kx. So that's kind of quite handy. But here's my tip: put a d in there as well, because the d then cancels the d there. Okay, so you get a d up in the exponent with the time dependence here. Okay, so what does that mean? That means that t of t is going to be e to the minus k squared d times little t. All right, but you can cope with having the diffusivity up there in the exponential for the time dependence. But for the radial equation, 1 over big R 1 over r squared d by dr. I get that. Okay. And now the diffusivity is and that saves me some effort, because otherwise I'll be writing square root of d for the next 3 pages of algebra. Okay, you know separation of variables always leads to lots of algebra. So actually just thinking ahead, knowing what the answer kind of is before you start, knowing to put a minus sign in there, knowing to include the diffusivity in the separation constant, will just make the algebra and make you much less prone to making mistakes. Okay? Do you know what you'd, final thing, do you know what you'd do last with that thing? Do you know how to simplify this? Go on.
Do you write it in terms of a variable, just like little r times big R? You can make it in terms of one, I think, anyway, or...
Yeah, you can. Yeah, good.
Usually turns into something nicer.
Okay. This, I think, is what you meant.
Yeah, yeah, something like that.
Let's try writing it like this. Is that what I want? No. Tell you what, you know, I can never remember whether it's multiply r or divide r. Actually I can, but let's pretend I can't. Okay, let's just put that in. R to the n, okay, times u of r. So dr, d big R by d little r, is going to be nr to the n minus 1 times u, plus r to the n times u prime. R squared d big R by d little r gives me that, and then differentiate again, gives me n plus 1, this is looking promising, r to the nu plus n plus 2, r to the n plus 1, u primed plus n r to the n plus 1 u primed plus r. Have I done that right? Have I managed to do the product rule correctly twice in a row? You're not shouting at me yet. Okay, I'll take that silence as an idea that maybe I did it right. N times n plus 1 times r to the nu. Let's collect the u prime terms together. 2 lots of n plus 1. Okay. And then if you really want to, 1 over r squared d by dr, but you can already tell what's happening here, yeah? Is n plus 1 r to the n minus 2u plus 2 n plus 1 r to the n minus 1 u primed. Yep. So what's the value of n you want to choose? What value of n? What? N is minus 1. Kills that. Kills that. Yeah. And leaves you, in other words, this equation simplifies. If I do this, then I'll end up with r of r is u of r divided by r, and the equation is 1 over r, so that's little r over u, and then this one, all of this 1 over r squared, all of this stuff here simplifies to give me u double primed over r is minus k squared. Okay, so the r cancels top and bottom, and hey presto, u double primed plus k squared u is 0. That's easy. U is A sine KR plus B cos KR. Okay. So a general solution, obviously big R is that expression divided by little r. And if I was solving inside the interior of a sphere, what would that mean? If I was solving inside a sphere for a spherical region, including the origin out to radius A, what would that mean for this general solution here? B would have to be 0 because the concentration is proportional to big R. And so as little r goes to 0, that goes to 0, that goes to 1, which means big R goes to B over little r as r tends to 0, the concentration would become infinite. It would not be a valid solution. So if you're solving for a domain which is the interior of a spherical region that includes the origin, then you can't have any b equals 0. In fact, the only solution you can have is sine kr over r, and that's actually sometimes called a spherical Bessel function. Okay, a little bit of information. J naught of x is sine x over x. And that is the spherically symmetric solutions to Laplace's equation are in fact spherical Bessel functions. Okay, and the 0 actually is L equals 0. It's an angular momentum thing. So that's why the solution looks like that. Okay. So there's a practice question on the example sheet, just to make sure that you're all happy with method of separation of variables. And in spherical polars, it's just being aware that a judicious choice of your separation constant, and then this substitution here makes it a whole lot easier to solve the equation. Otherwise, you wouldn't recognise that this equation here is kind of, well, the equation that you get from there is actually Bessel's equation for a fractional index. Okay, wouldn't expect you to remember that. But actually, you don't need to know any of that stuff about those funny functions if you remember about this this trick here. Okay. All right. Enough of that. How are we doing time? Oh, let's have a break. Okay, so typically separation of variables, as we've seen, works where at least one of the dimensions is kind of finite in extent. That's because you've seen that you always get some sines and cosines there, and therefore you typically use Fourier analysis on that, or something where the boundary condition actually restricts the values of the separation constant. So you'd find actually that k had to be proportional to, an integral times pi divided by the spatial extent of the domain. Okay, and that means you can write down a general solution. I want to consider the case now where we have an infinite domain. So we've got time variant, full diffusion equation. We're going to have an initial boundary condition, so we're going to specify what the concentration profile looks like at t equals 0, and now we want to know what it does now throughout all space. Okay, so to write down the equation, yet again, there's the equation I want to solve for C, which is a function of x and t. Okay, so x is allowed to go from minus infinity to infinity, and t goes essentially from 0 to infinity because we're going to specify C at x and t equals 0, okay, as a function. If I Fourier transform with respect to spatial position, okay, so you're happy about what that would mean? That would normally mean that I define a seed twiddle of k and t, which is the integral minus infinity to infinity. Everyone happy with that? I'm just writing down my definition of a Fourier transform, just so you can see the sign convention there and the normalization convention that I'm using. There, as you may be aware, in Fourier transforms there's a variety of conventions you're allowed to use for that, so I'm just writing down what I'm doing here. Okay, so if the right hand side is the easiest side to deal with, because of course here I've got a time derivative and I'm trying to do a Fourier transform which involves integrating with respect to x. And if this Fourier transform exists, now that if we always need to remember, for this to exist, this requires, strictly speaking, that this integral be absolutely convergent, yeah? Okay, remember that's actually the mathematical requirement for the Fourier transform to exist. Okay, because the Fourier transform is essentially the limit of the sum, and the phase factors there, they've all got modulus 1, haven't they? So when I look at the absolute value of this integral, this is what I get. And actually this isn't a problem for us. Concentration is always a positive thing, so actually the modulus signs aren't doing anything there. And the integral is that's just the total amount of stuff. So we're just saying we've got a finite amount of stuff that we're allowing to diffuse in this system. Okay, so actually there's no problem satisfying this condition in practice under these circumstances. The left hand, so the right hand side just becomes dc tilde by dt. So I'm using this tilde to denote a Fourier transform with respect to spatial position. Is everyone happy with that? Yeah? And on the right hand side, I just get that. Everyone happy? I've done that quite. Do you remember Fourier transforming a derivative? You get ik times the Fourier transform, don't you? That's the whole advantage of integral transformations. They turn differential equations into algebraic equations. And so if I do it twice, I get minus dk squared. What shall I do for time? Fourier transform with respect to t. Possibly. But remember that t only goes from 0 to infinity. So a Laplace transform is more convenient. Okay? So Laplace transform with respect to t. And C hat of x and s, I'm going to call, so would mean integrating from 0 to infinity c of x and t times e to the minus st dt. Okay, But here I'm not Laplace transforming C, I'm Laplace transforming C tilde. So this time, the Laplace transform with respect to t, it's only C tilde that has any t dependence here. So I'm going to get minus dk squared C tilde hat of k and s, a doubly transformed concentration. And the right hand side, I now have to Laplace transform a time derivative, and if you remember, that gives me s times the Laplace transform of the thing I'm interested in minus the function at t equals 0. Okay? Has everyone seen differentiate Laplace transforms of derivatives? Yes? Question? No? Okay. Good. If you're, you know, if I'm making wrong assumptions here, it's better that you say than I just plough on. But on the other hand, if you've got a cohort of generally able people who've seen this sort of stuff and are willing and able to tell you about it, you're probably best asking them as well. So this is why for this particular situation where I've got a differential equation with this initial value condition, why this combination of Fourier and Laplace works out, because now actually it is now just a I can just make C tilde hat the subject of the equation like this. Okay, and you see how the boundary condition, the initial value boundary condition, is now kind of in the solution. This is just what I would get by taking my initial value condition and Fourier transforming it. So I built in my boundary condition into my solution here. I've done it a bit as well. When I Fourier transformed, I implicitly assumed that the concentration and its first derivative vanished at infinity. So there's a number of things that I've done there. Okay. All right. Now, a little aside that will help us here. As you know, the thing about the Laplace transform is it's a bit of a pain to invert. You can do it with a Bromwich integral, but not everyone I would expect to have seen a Bromwich integral. So what you have to do sometimes is guess or look up in a dictionary. So a little aside is that if I take the Laplace transform of e to the minus alpha t, then that of course is just a very simple integral, which is minus 1 over alpha plus s okay, and assuming that alpha is positive and s is positive, then as t tends to infinity, this always disappears to 0, and when t is 0, this is just 1, and that's the lower limit, so it comes with the minus sign, which cancels that. So I just get 1 over alpha plus s. I'm sort of, actually we want both s and alpha to be positive there. Okay, so if you compare that with what I have here, you see that I have something that doesn't depend upon s, so this is just a multiplicative constant. So that tells us that we can write down, okay, we can inverse Laplace transform now and just get that this is c tilde of k and t is 0 times e to the minus dk squared t. Okay? And that of course is familiar. That's what we saw something very similar from the separation of variables. So perhaps not a complete surprise there, but notice here that k in here The k before in separation of variables was just a separation constant. K here is the complementary Fourier variable, which actually is masking some spatial dependence. Yeah? Okay, remember k was in the separation of variables again, k represented the spatial frequency of the sine and the cosine. And so what this is actually saying is this is saying that higher spatial frequencies, smaller wavelengths, decay in time more rapidly. And that's a feature of diffusion. Okay, so although this looks, in terms of algebra written on the paper, almost exactly like the separation of variables, and it has something in common with it, it's not quite the same thing. In the separation of variables, these are constants that are selected to match boundary conditions. Here it is a continuous variable, which is basically some spatial dependence. So it's not quite the same. That is a product. If I wanted to invert the Fourier transformation, what will I get? If I inverse Fourier transform a product, convolution, so C of x and t must be C of x at t equals 0, our original boundary condition, convolved with the inverse Fourier transform of that function. Okay? Let me just go over this page. Let's just do something separate for a minute. Let's just think about the inverse Fourier transform of e to the minus dk squared t. Do you know what that is? Do you know what the answer is? What is the function? The function of k you want to do. How would you describe it? Gaussian. What's the Fourier transform of Gaussian? It's also a Gaussian. So you know the answer. Have you ever proved that? Have you proved it properly? I wonder whether you really have proved it properly. Let's just check this, okay? What I mean is without mathematical dodges. You'll know by the end of this whether you have or not. Okay, this isn't massively important, but just be aware. So according to my normalization convention, the inverse Fourier transform has to have a 1 over 2 pi out the front. Then it's got this. Then it's got the function that I'm wanting to do. And then I must have an e to the minus ikx in the front. And then I'm integrating that with respect to k. Yeah? Happy with that? And what do I do? The way you do this is you write this as the exponential. You complete the square. Whoops. Okay, so you complete the square in here. So when you square up, you get k squared, which gives you minus dk squared t. So you get that term from squaring up the first bit here. And then the cross term is twice k ix over 2 dt. So the twice cancels the 2 down there. The dt cancels the dt out there. And you end up with ikx with a minus sign. So you get that term there. And then you end up with a minus x squared over 4 dt squared times dt with a minus sign in it. The minus sign and that I squared gives you an overall plus sign, and that's the thing you don't want, so you have to subtract off x squared over 4 dt. Okay? dk. And then you say, oh, happy days, look, there's my Gaussian that I wanted. Okay? So I can take this out the front, I can say this is 1 over 2 pi e to the minus x squared over 4 dt times the integral here of x minus dt k plus ix over 2 dt all squared dk. Yeah? and then you'll just say that's a constant, right? Sorry? I can do what, sorry? Yeah, okay. So the issue is, if this was a normal integral where this was just k, right? What you want? Sorry, let me try and explain this. Well, let's do a change of variable. Z is k plus ix over 2 dt. Yeah. So it's an integral over k. So ix over 2 dt is a constant. So dz is dk. Then the integral would be 1 over 2 pi e to the minus x squared over 4 dt integral minus infinity to infinity e to the minus dt z squared dz. Right? Right? Okay, smile there, shake of the head there. Okay, shake of the head. Why?
Because you need to have an imaginary part of the
Yeah, thanks. Some people clearly have done this. So I have to have ix over 2 dt there and ix over 2 dt there. In other words, in the complex plane for z, my integral that I'm doing here is running along this line here, where the imaginary part intersects there, like that. This is the real part of z, this is the imaginary part of z. Okay? Whereas the integral that I know how to do runs along there, right? So what do? We close it up like that, and we say that, and we say let's consider this one. And this integrand here is perfectly analytic. So by Cauchy's theorem, around this contour C, e to the minus dt z squared dz must be naught. Yeah?
How can you say it's analytic if the curves at the edges are minus infinity?
Okay. Let's just think about those. So the function is analytic everywhere in there, in the finite domain, and admittedly it might do something slightly strange within a singularity at infinity. So let's just ask ourselves about the singularity at infinity. If z squared has an imaginary part, that just causes the thing to oscillate. Yeah? So any imaginary part doesn't change the modulus of the function. So if z squared, so what we need is that the real part of z squared had better be positive. Yeah? If the real part of z squared is positive, then clearly the integrand is going to 0 down over here and over here. Okay? And the real part of z squared, okay, so if z is got a real positive part, then it's going to decay there as long as its imaginary part is not bigger. But its imaginary part is finite here. Yeah? With a slight worry as t tends to 0 or x tends to infinity. Yeah, as x tends to 0 or t tends to infinity, this point moves up and the imaginary part of z gets very large. Okay? At which point I might worry, in the real part squared minus imaginary part squared, bit which is the real part of z squared, does the imaginary part win? But the reality is I'm going out in this direction first. Okay? So over here and over here is exponentially small, the integration over there, so I don't get any contribution from those parts. It is a slightly subtle point. You're right to ask. Yeah? But essentially, that tells me that the integral along this displaced horizontal line is the same as the integral along the real axis, and therefore, in fact, I can ignore those, say that it's the same. And then, of course, it is just the standard result, isn't it? So it is 1 over 2 pi e to the minus x squared over 4 dt times now root pi over root dt. Yeah, standard result for the integral of a Gaussian. And so overall, the solution is 1 over the square root of 4 pi dt e to the minus x squared on 4 dt. Okay, so that is in fact essentially a normalized Gaussian. Do you see what happens here as time is progressing? As time is progressing, the variance of the Gaussian is getting larger, isn't it? But also the peak is reducing in height. And it is doing so in such a way that the total integral of the concentration is going to remain constant. Okay, so we come back over here. All right. And it turns out that this is going to be, so when I put it back in the convolution now, here's the square root normalization thing that's come out of this inverse Fourier transform. And now the convolution involves an integral like this. Okay, that is the form, that's the convolution that I get out when I just apply the Fourier convolution theorem. Okay. And I won't bore you with proving that unless you really beg me. To understand what this is, let's put C of x at t and 0 equal to some amount of stuff with a Dirac delta function at position x0. Okay, so if I integrate that concentration, I would just get big N. And then, of course, what that means is I've got a Dirac delta function in my integral here. So I'm only going to get contribution when x primed is x naught, and then it's just going to give me that there. And so C of x and t under that instance is n over root 4 pi dt times e to the minus x naught all squared over 4 dt. Okay, and this is important. This is called the fundamental solution for the diffusion equation. Okay, you're used to fundamental solutions. So in electrostatics, you solve Poisson's equation. You have a point charge source on the right-hand side, and it gives you the Coulomb potential. Here, the fundamental solution operates a little bit differently because you've got an equation in space and time here. So here what we're talking about is the solution in time where I have a sort of point concentration distribution at t equals naught. And I'm asking how that evolves later in time.
Negotiate this with a root function of the...
You need to be a little bit careful because, of course, remember that a green function is when you have a homogeneous differential equation, but you replace the right-hand side with a Dirac delta function. So you have an instantaneous, you have an impulse right-hand side. Now here in the diffusion equation, there's nothing ever in the diffusion equation that looks like delta. The delta is in the boundary condition. So it's not strictly a green function, but it is very, very similar in approach.
I see so you have your solutions here, right?
Yes.
And on the right hand side, you're saying you're okay, it's not your homogeneity, it's just
what I'm doing now, but you can see what's this formula is this taking? Well, actually, let's come back to that in a minute. Let's just make sure we understand the form of this fundamental solution. So very quickly, let me just draw the graph. Let's put the point x naught here. Okay, so at t equals naught, yeah, that's what it looks like. Obviously, there's an infinitely large spike. Okay, all of the material, all n of it at point x naught. And then at some short time later, okay, it's broadened into a Gaussian like that. At some time a little bit later, oh, that's badly drawn. That's really quite badly drawn. I would expect you to do better than that, so I better do better than that, hadn't I? Just not sure, that's still not brilliant. Do you know what I'm trying to do here? I'm trying to get the area under these curves to be constant, because it always needs to integrate to n, and I'm not doing a very good job. Okay, but as time increases, you see what I mean? It gets broader, it gets lower, such the area remains the same. So that's what a point source does. Okay, from some point x naught. And the point is now we exploit the linearity of the diffusion equation, that we can superpose solutions. So what we do is we consider essentially representing our initial concentration profile as broken up into a series of Dirac delta functions. And then we say, well, the diffusion equation will evolve each of those into Gaussians that get broader with time. And so we can then just superpose those Gaussians at a later time, and that will give us actually what that concentration profile has done. So it's very, very similar to the approach to the Green's function, but it's just not strictly a Green's function.
yeah, because
That's why I called it the fundamental solution.
The integral looks very similar.
It looks exactly.
It's not a homogeneity in equation.
It's a boundary condition, but it's the same, essentially the same Green's approach applied to treating the boundary condition, an inhomogeneous boundary condition, rather than an inhomogeneous right-hand side of the equation. Exactly. Okay. Okay, so what can we say? We see that the variance of this Gaussian is 2dt, so increases with time, as I said. Okay. And now you see how things get smeared out, how the diffusion equation tends to smear stuff out. So this is why the short wavelength variations get washed out very quickly, because in an amount of time, so sigma squared is a length squared dimensionally, in a time 2dt, you've smeared out, all of your Dirac delta functions are smeared out now to width square root 2dt. So any variation in the concentration profile that is shorter in its length scale than square root 2dt will have been disappeared, because it's been smeared out into Gaussians on that length scale. But obviously a much longer wavelength variation, you're going to have to wait for a much longer time t before you're able to wash that out. So you can see how that happens. Now, just some other things to point out. We've solved this problem for the infinite domain in space, from minus infinity to plus infinity in space, and from 0 to infinity in time. So strictly speaking, that's how we can use it. But it is worth noting, it's symmetric about, the fundamental solution is symmetric about the point x0. Do you see the flux is 0? Because the gradient of c is 0, dc by dx is always 0 at x equals x0. That means that, if you like, after the initial sort of instant at which point all of the material, some of it has moved right a little bit, some of it's moved left a little bit, from that point on, all of the material to the right kind of stays on the right and all the materials to the left stays on the left. It's symmetric. There's no net flux across the boundary, okay, across x equals x0. And that is just worth pointing out, therefore, that if you were trying to solve the problem for a semi-infinite domain, okay, with an initial concentration on the surface, and you had no flux across the surface, then this would work as a solution for that problem. The only thing you'd have to do is you'd have to put a factor of 2 in, because now all of the material, okay, that is on the surface, x0 at time t equals 0, all of that is now going to diffuse into the right, whereas previously half of it would have gone to the right and half of it would have gone to the left. So there is a little bit. And of course that's how you often measure diffusivity. You deposit a thin layer of material on the surface. Typically it might be radioisotopes. So if I've got if I've got some gold, I put some radioactive gold on the surface, and then I heat it up and leave it for a long time, and then I can sort of measure the isotope concentration profile throughout the sample by measuring its activity at a later time. Okay. Just to finish up then, we're not going to go through this, but let's just tee up where I want to go next time, because we haven't got time to get far enough with this. We've seen that there's a sort of, it's not an analogy, but it's a connection between the Green's approach and the fundamental solution for electrostatics. How else do you get solutions in electrostatics? What other methods are you aware of?
Images?
Method of images. Do you remember that? When you have a semi-infinite domain, you have an image charge. You know, heard of image charges? There's a way, okay. If you have, that's great. If you haven't, doesn't matter, because we'll go through it. But essentially there is an equivalent of the method of images that we can now use to employ this fundamental solution to solve more complicated sort of shape domains. And we'll look at that next time. Okay. And I think actually, looking at the problem sheet 2, you will need, you can't, I don't think you can do that one yet. Okay, so don't get too excited about that. The other questions you probably can, but I think that's enough for today. Okay, thank you very much. Am I seeing you on Friday?